In topology, connections matter more than the shapes of figures. Have you ever pressed a balloon with your hands? A balloon can become flat or stretched into a long shape. However, no matter how much its shape changes, it is still the same balloon. Clay works the same way. We can shape it into a round form or stretch it into a long one, but as long as we do not cut it or attach it to another piece, it remains the same clay. There is a field of mathematics that focuses on connections rather than shapes. It is called topology. To solve the Königsberg Bridge problem, Euler removed all the details of the actual city. He ignored the shape of the river, the length of the bridges, and the distances between locations. He focused only on which locations were connected by which bridges. A diagram that represents only these connections using points and lines is called a graph. In a graph, it does not matter whether a line is straight or curved, or whether it is long or short. The only thing that matters is how the points are connected. Euler's idea later led to the development of two new fields. They are called graph theory and topology. Graph theory is a branch of discrete mathematics that studies connections, shortest paths, networks, and related structures. Topology, on the other hand, studies properties of figures that remain unchanged even when the figures are stretched or bent. In graph theory, two graphs are called isomorphic when they have exactly the same number of points, the same number of lines, and the same connection structure. Topology has a similar concept called homeomorphism. Imagine a mug made of clay. If we smoothly stretch the handle and reshape the body of the mug, we can transform it into a shape that looks like a donut. As long as we do not cut or attach any part, there is still exactly one hole from beginning to end. For this reason, topology considers a mug and a donut to be the same figure. A soccer ball, however, cannot become a donut no matter how much it is pressed or reshaped. A donut has one hole, while a soccer ball has no holes. Creating a hole would require tearing or puncturing the figure, so the two figures have different topological properties. In mathematics, this relationship is also defined using functions. If every point of one figure corresponds to exactly one point of another figure, and this correspondence remains continuous in both directions, the two figures are called homeomorphic. Simply put, if two figures can be transformed into each other by smoothly changing their shapes without tearing them apart, they have the same topology. Then how can we distinguish the topology of different figures? This is where the Euler characteristic comes in. If the number of vertices of a polyhedron is represented by V, the number of edges by E, and the number of faces by F, the Euler characteristic can be calculated as V minus E plus F. The Euler characteristic of all plane figures is 1. For example, an equilateral triangle has 3 vertices, 3 edges, and 1 face. Therefore, its Euler characteristic is calculated as 3 minus 3 plus 1 equals 1. Squares and even concave polygons also have the same result, which is 1. For 3-dimensional figures, the situation is slightly different. The Euler characteristic of any convex polyhedron without holes is 2. For example, a cube has 8 vertices, 12 edges, and 6 faces. Therefore, its Euler characteristic is calculated as 8 minus 12 plus 6 equals 2. Even if a cube is reshaped into a sphere or a cylinder like clay, its Euler characteristic remains 2 as long as no holes are created. Although their shapes are different, they all have the same topology. Then what about a 3-dimensional figure with 1 hole, like a donut? If we divide the figure into smaller faces to calculate its structure, it has 16 vertices, 32 edges, and 16 faces. Therefore, its Euler characteristic is calculated as 16 minus 32 plus 16 equals 0. When one whole is added, the Euler characteristic changes as well. Topology uses these values to distinguish the structures of different figures. Today, topology is not simply a field that studies figures. It is used to analyze connection structures when designing subway systems, study how proteins fold in biology, and explain the structure of the universe in physics. Recently, topology has also become important in artificial intelligence. By analyzing complexly connected data using topology, researchers can discover hidden structures and transform data into forms that are easier to process, improving learning speed and accuracy. About 250 years ago, Euler's simple idea of finding a way to cross a few bridges grew into a fundamental area of mathematics that now powers artificial intelligence and advanced science.